Hello and welcome to the video lecture on organic synthesis and retrosynthetic analysis. Today you are going to talk about the retrosynthetic analysis of 1,6 bifunctional compounds, more precisely 1,6 dicarbonyl compounds. As we know, 1,6 bifunctional compounds represent a dissonant target class, and therefore their disconnection generally will involve Ampolang synthons, and they are considered to be a little bit difficult to synthesize because of the greater distance between the two functional groups. এর আগে এতটা ডিস্টেন্স আমরা কোনো টার্গেট মলিকিউলে দেখিনি। 1,3, তার আগে 1,2, 1,4, 1,5, সবার থেকে বেশি বড় ডিস্টেন্স উই হ্যাভ হিয়ার বিটুইন দ্য টু ফাংশনাল গ্রুপস। And because they are dissonant systems, as I have said, Ampol strategy will have to be employed if I am going to disconnect them in the conventional fashion. Conventional fashion disconnection কতগুলো দেখানো হয়েছে. So first we get a disconnect right next to a carbonyl and then assign a plus charge to the carbonyl carbon to give you the A1 synthon, and the other part is obviously D5, which is illogical. That would come from the corresponding bromo-keto compound via organometallic transformation, that is ampola, but in that case the carbonyl needs to be protected in the form of acetal. After forming the acetal, you can add the zinc here, therefore this carbon will alter its polarity from electrophilic to nucleophilic, and you can add a A1 synthon such as a aldehyde or a ketone or a acid chloride to access either the alcohol or the carbonyl, or you could add a nucleophile onto this so that an SN2 reaction takes place, so that you again can establish 1, 2, 3, 4, 5, 1, 5 relationship, but that you can do in other ways as well. This delta bromo ketone, that needs to be protected, otherwise the self condensation will take over while forming the organogen compound. Same disconnection, but this time altering the charge pattern, revealing a D1 illogical synthon and a A5, that is a logical electrophile. But D1 is illogical. We know we can use, obviously we can use nitroalkanes or etc., so that finally the carbonyl may be revealed, and this A5 will be represented again by the delta bromo ketone. Protection will be required here because otherwise the reaction may even take place at this point. 1,6 dicarbonyl R1 R2 disconnect between C2 and C3 to reveal a D2, which is a logical one, and A4 illogical one. So considering it as a derivative of R1CO CH3, therefore I will be needing as a D2 synthon beta keto ester. And this A4 illogical synthon, that will be coming from gamma bromo ketone, which is a 1,4 bifunctional target molecule. We have already synthesized that. Again, we will need protection here for the nucleophilic displacement to take place, otherwise the reaction may as well happen here. Altering the charge pattern, making the A2 illogical synthon combining with the D4 logical synthon. This A2 illogical synthon is obviously alpha bromo ketone coming from the corresponding ketone ampolan here, and this time D4 is obviously again the gamma bromo ketone. For via organometallic reagent, protection will be required so that self condensation can be avoided. This time we are moving one carbon further away from the carbonyl site and disconnecting between C3 and C4. So like middle of the 1,6 network. One will be minus, that is the D3 illogical, the other will be A3 logical, and D3 illogical. This time I need a leaving group here so that I can get a beta bromoketone. That's a 1,5. That's a 1,3 difunctional target, which we can generate by adding HBr across the double bond of an enone. And to displace this leaving group, we are going to need an organometallic reagent here, so that can be derived from the beta bromoketone itself. But the beta bromoketone needs to be protected here, forming the organometallic, otherwise self-condensation will take place. However, by this time you should be convinced that none of these strategies look very promising. They not only involve Ampolong reagents, but also are very elaborate. They will require lots of protection and deprotection steps, which will eventually compromise the yield. And therefore, this target molecule, where the two oxygenated functional groups have largest through bond distance, that is, we have seen till now, uh, is better prepared by something which is known as the strategy of reconnection. That means join the two oxygenated carbons by removing the double bonded O functionalities and put a polyphenic double bond between those two carbons, so that you get a 6-membered ring with double bond, which can be oxidatively split with processes such as ozonolysis that also offer you the freedom to work the reaction mixture up with various different reagents, eventually leading to the desired oxidation state at that particular carbon, which was double bonded in your reactant but has been oxidatively split in the product. That means ওজোনোলিসিস করো এবং ডিফারেন্ট ওয়ার্কআপ প্রসিডিওরকে অ্যাডপ্ট করে তোমার টার্গেট মলিকিউলে যে ধরনের অক্সিডেশন লেভেল চাইছে, কার্বক্সিলিক অ্যাসিড অক্সিডেশন লেভেল চাইলে সেইটা, অ্যালডিহাইড চাইলে অ্যালডিহাইড, কিটোন যদি চাই তাহলে কিটোন, তাহলে সেই রকম অক্সিডেশন লেভেলটাকে অ্যাক্সেস করো। So that is the strategy of reconnection. That's not a disconnection, that's actually basically removing two carbonyl oxygens and then joining up these two carbonyl carbons. And this we have seen previously. In one target molecule, we were trying to synthesize a carbonyl compound like that, and we thought that this could be coming from a molecule such as this and oxidatively splitting this one. So we are familiar with the strategy of reconnection in that sense, but this time we are taking it even a bit further. Let us take a few examples. Think of adipic acid. How can you synthesize adipic acid? It is best prepared from cyclohexene. If you redraw adipic acid in such a way and then join these two carbons by removing the excess functional groups by a double bond, they will end up with a cyclohexene. This cyclohexene, upon ozonolysis and work up with aqueous H2O2, will give you this compound. And if you don't want this CO2H to be forming here, then you can properly choose the dimethyl sulfide or zinc workup, so that the two CO2Hs are now CO2CHO. So you can get a dialdehyde as well. How can you get cyclohexene? Cyclohexene is very easily prepared from cyclohexanol, which is very easily prepared from phenol via reduction with hydrogen nickel. And phenol is a byproduct of the coal tar, or you can access phenol via the cumene phenol process. Cumene is derived from benzene and propene. So that is a very, very abundant source of the 6 carbon units attached in a cyclic fashion. And once you have that, you can just cleave the carbon-carbon double bond to access the 1,6 difunctional, more precisely 1,6 dicarbonyl compound. Consider a 1,6 bifunctional compound where one part is a carboxylic acid, the other part is a ketone. Therefore, you will need a 7 carbon unit where we have a 6 carbon cyclic structure with a double bond, and the double bond is right next to the methyl. Therefore, that's basically 1 methyl cyclohexane. How can I get this thing? This is coming from obviously a dehydration reaction of 1-methyl cyclohexanol. Now, this 1-methyl cyclohexanol will be coming from corresponding Grignard reagent, methyl magnesium iodide and cyclohexanol, that is revealed by the HOCC disconnection. Obviously, this will be coming from the cyclohexanol. Cyclohexanone is coming from cyclohexanol, and the cyclohexanone can be easily generated, eventually traced back to the cumene phenol process. So that's very good. Remember, এখানে কিন্তু আমরা এইখানটায় OH অ্যাড করিনি, কারণ এখানে যদি আমরা OH অ্যাড করতাম তাহলে কিন্তু অ্যাম্বিগুইটি চলে আসতো। ডাবল বন্ড এদিকেও পড়তে পারে, সেট যে হপম্যান প্রোডাক্ট ডাবল বন্ড এদিকেও পড়তে পারে, মিক্সচার অফ প্রোডাক্ট হবে। ওই জন্য ইচ্ছাকৃতভাবে OH-টাকে এখানে অ্যাড করা হয়েছে যাতে কোনো অ্যাম্বিগুইটি না থাকে। এখানে যদি তুমি OH অ্যাড করো তাহলে এদিক থেকে গেল কি এদিক থেকে গেল, ডাজন্ট ম্যাটার, ইউ উইল অলওয়েজ গেট দি 1-methyl cyclohexane. Okay. This target molecule does not look like a 1,6-dicarbonyl, but once you disconnect with the alpha beta, you will be getting a 1,6-difunctional compound. So adopt the strategy of the reconnection. Fine. If we do that, then we will have a cyclohexene derivative. Here, 1 number position at a methyl আছে, 4 number position at a tertiary butyl group আছে. Okay, so double bond is coming from the corresponding alcohol. HOCC disconnection reveals cyclohexanone derivative. Here, 4 number position at a tertiary butyl আছে. Think of a FGI oxidation. So this becomes OH, then this ring is aromatized in terms of retrosynthetic analysis. So in the forward direction, you will have to destroy aromaticity. That can be done, and particularly so when you have a phenol. So you have now a phenol where the fourth position is there is a substituent, that's a tertiary butyl. So 4-tertiary butyl phenol, which you can access from the Friedel-Crafts acylation or Friedel-Crafts alkylation on phenol with tertiary butyl chloride. The para product will be the major, or could be even the exclusive product, considering the ortho product would be very crowded. One thing you need to remember, যে reconnection strategy adopt করা হয়েছে, ozonolysis যখন করা হবে তখন you will need to have the aldehyde oxidation level here, যাতে কার্বক্সিলিক অ্যাসিড না হয়ে যায়। সেই জন্য আমাদের এখানটায় নন অক্সিডেটিভ ওয়ার্কআপ করতে হবে, লাইক অনেকে এটাকে রিডাকটিভ ওয়ার্কআপ বলে, বাট প্রিসাইজলি ইট ইজ নট রিডাকটিভ, কারণ রিডাকশন তো কিছু হচ্ছে না। এমন নয় যে আমি এখানে প্রাইমারি অ্যালকোহল পাচ্ছি, আমরা যেটা ওভার অক্সিডেশনটাকে অ্যাভয়েড করছি, সো সেটা আমরা ডাইমিথাইল সালফাইড বা জিঙ্ক দিয়ে করতে পারি। Okay, so this is a meso compound. As you must understand that you can pass a sigma plane through here, and it's also 1, 2, 3, 4, 1, 4 difunctional. 1, 2, 3, 4, 1, 4 difunctional, but at the same time 1, 2, 3, 4, 5, 6, 1, 6 difunctional unit. So let's just first remove the esters. Do an FGI esterification. So get a 6-membered ring. So get a 1,6 dicarboxylic acid. Then remove the ethers so that we have now CH2OH groups here, and now do the 1,6-dico reconnect so that a cyclohexene derivative is produced where the 1, 2, 3, 4 and 5, these two carbons are attached to the CH2OH groups. You can do a very clever analysis here and think that both these arms are coming from this anhydride unit, because if you reduce the anhydride unit, then this will become CH2OH, that will also become CH2OH, and this time you understand that this is a target which can be derived from a Diels-Alder reaction between 1,3-butadiene and maleic anhydride, which represents the class of dienophiles that carry electron withdrawing group. Therefore, Diels-Alder reaction under normal electron demand will be very favorable, and then you just have to reduce these things, and then you have to oxidatively split this one, then etherify, and then esterify the whole thing to get this. Diels-Alder reaction is an excellent technique to construct 6-membered ring with 1 double bond, and particularly with very large amount of stereochemical control. You need these two to be cis to each other, and as Diels-Alder reaction is supra superficial interaction. That means when these two are like C's with respect to the double bond, they will remain C's in the product or the Diels-Solder adduct. So you can adopt this retro Diels-Solder strategy here with great amount of success. Okay, another 1,6 bifunctional compound, carboxylic acid. So just draw it by bringing this thing here and then reconnect. So get the 6-membered ring with a double bond, and this tertiary amine now can be derived from the corresponding ketone and the N-methylalanine via a reductive amination. So you are forming the imine in situ and then you are reducing that as soon as it is forming by reducing agents such as sodium cyanoborohydrate or something like that. So Bort's reductive amination you are doing. This one is obvious target for Diels-Solder, again 1,3-butadiene plus methyl vinyl ketone that represents the dienophile with electron withdrawing. Okay, this one is a little bit tricky. I can't see the 1,6 relationship. Neither can I see any other relationship. So first let's disconnect the ester so you get the corresponding secondary alcohol. Now this could be derived by reducing a carbon-carbon double bond. And once you reduce the carbon-carbon double bond, so you have in your target, you have this carbon-carbon double bond, you can think that we are making this double bond by a Wittig reaction with a proper Wittig reagent derived from CH3I, and we have a carbonyl here. So if this Wittig reagent reacts with this, then this will be, converted to the carbon-carbon double bond. And now we have the 1, 2, 3, 4, 5, 6, 1, 6 bifunctional relationship. If I am to, you know, uh, if I am to uh, join these two things, I could get this from the lactone. But you might ask that if I have a lactone and if I hydrolyze that, then this will be like carboxylic acid, no? This will be alcohol, this part will be alcohol, but this will be carboxylic acid. But I am not going to hydrolyze that. What I am going to do is just treat this with RLI. So what will happen? If I treat this with 1 equivalent RLI, then this will react here. This will open up, this will close down, and this will be liberated in the medium, so that I will get a RCO at this carbon and I will get a lithium alkoxide at this carbon. And then I can do the proper Wittig stuff. Why did I do that? Because this is a 7-membered lactone with 2 cis-methyl groups at the 1, 2, 3, 4, 5 and 6. This can be derived from the 6-membered cyclohexanone derivative via Baeyer-Villiger oxidation. When you do the Baeyer-Villiger oxidation on this target, on this particular target, this is where the oxygen will be inserted, because Baeyer-Villiger oxidation is migration of something from carbon to electron deficient oxygen, and as a result that group will migrate, which is more substituted and more electron releasing. So this is where this double bond will be, this oxygen will be inserted. And moreover, Baeyer-Villiger being an intramolecular rearrangement, the migrating group will retain its configuration. So the configuration that I am seeing here will be replicated here. How can I access this one? I will have to do a full reduction of the aromatic ring of the 2,3-dimethyl phenol. So from a easily available starting material, we can access this complicated looking thing where R is N-octyl. So I have used the N-octyl lithium to introduce the R group here, but the main carbon chain is constructed from the phenolic compound. Okay, so this is not very easy, and if you are not experienced in this kind of disconnections, this does not become apparent, but with practice you will be able to see this pattern. This one is very famous because it is one of the starting materials or monomers for the nylon 6,6. That's the epsilon amino caproic acid, and you can synthesize it from the corresponding caprolactam, that is cyclic amide, by disconnecting the CO and reconnecting this carbon with this nitrogen, so that you get a 7-membered lactam, which is the epsilon caprolactam, which is again the monomer of nylon 6. Now if you disconnect this whole nitrogen thing and reconnect C1 and C6, that's basically insertion of nitrogen or NH between the C1 and C6 in the forward direction. That is nothing but Beckmann. That is nothing but Beckmann. And Beckmann, you can do it, you can do on the corresponding oxime. So that's not the cyclohexanone that you immediately get. It is the oxime of cyclohexanone, which you can eventually derive from cyclohexanone. And cyclohexanone you can derive from cyclohexanone. So cyclohexanone going over to oxime, oxime rearranging via Beckmann rearrangement to epsilon caprolactam, and then hydrolyzing. So we have used one rearrangement here, Baeyer-Villiger, and this time we are using the Beckmann rearrangement. This one already has the 1, 2, 3, 4, 5, 6, 1, 6 relationship, but the tricky part is the cis double bond. So think of it, do an FGL, make it CHO. After you make it CHO and then you redraw the whole thing, you can join up the C1 and C6 so that you have a double bond here. So when you ozonolize this will become CO2Me. A non-oxidative workup will ensure that this will become CHO. So you will get this. The only difficulty is that you have couple of double bonds here. Therefore, ozonolysis has to be carried out under selective condition, and this double bond, being the more electron rich of the two, will be selectively targeted. But this one is experimental condition has to be set up in such a fashion that this double bond, it does not get oxidatively split, and it can be done. It has been done. This is a literature report and a very famous work. So this has been done, and the attractiveness of this proposal is that you already have the cis double bond installed, so the stereochemistry is already fixed. And this one, you can understand that this is a Barch reduction product of this aromatic ether, which is directly coming from paracresol, which is easily available. So this is where the system becomes very, very attractive to the synthetic chemist, because he has paracresol, he can methylate it very easily, and once he has that ether, if he can set up the condition right for the ozonolysis, then he can directly access this substituted aldehyde ester, which can be further reduced to give you the corresponding target molecule. The reduction has to be chemoselective, so we are using sodium borohydride, which does not reduce the ester but targets the CHO. So there is a selectivity here. Ozonolysis needs to be selective. Can be done. This one being more reactive double bond, more electron rich double bond. It will be preferentially cleaved via ozone, but you have to set up the condition right. And here the reduction needs to be chemoselective as well. Need to use reagents. We do not react with ester, but reduces aldehydes. Okay, what do we have here? This one, we have seen this one. This one is a Claisen type target where there is no alpha hydrogen to pick off. So how can I synthesize that? We can do that via Claisen under acidic condition via the intermediacy of acyl cation, but that will give me a 1,6 dicarbonate. If I use the strategy of reconnection here, then that the synthesis of this compound is not very obvious, because I can put a OH here, but that may even lead to not the double bond here, but the double bond could be here. If I am getting something like that, then it's not good. If I am to push the OH here, then the double bond may not be here, double bond could be here as well. So that's not good either. So, and moreover, even if I have this OH, the synthesis is not very apparent to me. How can I do that? Therefore, the strategy of reconnection is not going to help you always. At least you are getting an example where it is not helping you that much. So think of the conventional disconnections. So disconnect it, reveal the D2 and A4. This A4 illogical electrophile will be the gamma bromoester, and we have prepared it before. Now this one is coming from corresponding gamma bromo acid, which is the alpha beta gamma. Gamma lactone when treated with HBr will give you the corresponding gamma bromo acid. The reaction is something like that. It will, it will be protonated here, and then you are attacking this bromide with this bromide here. So this breaks off, and this carbon becomes the carboxylic acid carbon, and this one is the alpha beta gamma. It is getting attached to the bromide. So you get the gamma bromo carboxylic acid. Esterification will give you the gamma bromo ester. Okay, and here we have the cyclopentanone derived anion. So I need to have this anion stabilizer CO2T so that I get a clean SN2 reaction here, and this will be coming from Dickmann condensation of diethyl adipate. This diethyl adipate will be coming from adipic acid, which was our first target molecule for today's lecture. So I am eventually using the reconnection strategy here as well, but not where you are expecting, but downstream. Down the line, I am using the reconnection strategy, but not where you expected it to happen. So the illogical electrophile being derived in relatively easy manner, this one is a better proposal corresponding with respect to the corresponding 1,6-dicarbonyl reconnect strategy, where we are getting an alkene, the synthesis of which is not very obvious for us. This one we have done previously. We did that by disconnecting the 1,3-dicarbonyl, replacing it with cyano, and then disconnecting the whole thing, making it OH here. First bromo, then OH, then this became CO2H, and then it was considered as a derivative of acetic acid, which means you could disconnect here. So that 2-carbon unit will be coming from the ethyl acetoacetate, and you had cyclohexenone. But if you were to adopt the newly learned reconnection strategy, you will be getting something like this, which is not good. This is very, very strained. The ring size is only 3, 3 and 2. Therefore, 8-membered ring with a methylene bridge cannot accommodate a double bond here comfortably, violating Brett's rule, and therefore this cannot exist. So the reconnection strategy is not good. But we have already solved that thing. Make it cyano, disconnect it here, make it bromide, then make it CH2OH, make it CO2H, and go for the 1,5-dicarbonyl. Here is another disconnection. If you don't remember that, then you could think of it in this way. So reveal the 1,6-dicarbonyl keto ester, and then do a FGI oxidation so that you may have the secondary alcohol here. If you have the secondary alcohol here, then put a double bond here, FGI reduction. It doesn't matter whether the double bond is cis or trans, but the preferred diastereoisomer is trans. So I have alpha beta unsaturated ester, and I can generate it from the corresponding carbonyl compound and diethyl malonate by a Nagel reaction. So that's basically meta-hydroxybenzaldehyde condensing with diethyl malonate. This meta-hydroxybenzaldehyde can be derived from the corresponding amine, where the NH2 is diazotized and then replaced by the OH. So diazonium route will work, and this one will be coming from the corresponding nitroaldehyde, where a chemoselective reduction has to be done. NO2 gets converted to NH2 via SnCl2 HCl, and then disconnect the CN to reveal the benzaldehyde, where CHU is a meta-reacting group and therefore directs the incoming nitroelectrophile at the meta position. So your regioselectivity is absolutely okay. So here you are, 10 target molecules that has within them very obvious 1,6 relationships or can be modified to manifest their 1,6 relationship. Here are 8 further target molecules for you to practice. So try to adopt the 1,6 dicarbonyl reconnection strategy for these molecules and see how things pan out. I hope that you have understood the lecture, and I thank you for your patience, and I will be seeing you in the next one, which will be based on protecting groups.